My name is Wang, come from CSIRO, and we are the Australian Government Department for Science. And today I'm going to introduce our work about it's called the DOITRUST. So it's about end-to-end solution about how to use the graph learning for a specific cybersecurity task. Here, the task is the web domain evaluations. So it includes the data construction, pre-processing, the feature engineering, model design, model training, and post-processing. The background is we are facing cybercrimes maybe every day. For example, we have 3 billion phishing emails every single day. And one of the most common tools of the cybercrimes is the use of malicious URLs and websites to carry out the malicious activities, right? And on the other hand, the allow list or block list is a very good solution to defeat the URL-based cybercrimes, right? And they are easy to use, but sometimes useless. The reason is the list itself is incomplete and passive, and their updates are always labor and time intensive. So, and maybe the list can be trusted at the beginning, and some of those got compromised after few months or years, right? So the question here is how to develop a dynamic and organic mechanism for expanding and monitoring the allow and the block list. So we can start from the list expansion, right? So given a seed list, for example, we have a collection of 50,000 trusted web domains, including the government, organization, official websites. And we can start from the querying the children URLs in the HTML of the main page of each domain in the list. And then we perform the breadth first searching interactively layer by layer until we reach the 6-layer deeps, like the children, right? And finally, we can extend the sheet to a graph with 1.7 million nodes and 12 million edges. So here the node is a web domain with the default web page, and the edge is the hyperlinks to link different web page. So the good news is now we have an extensive graph and we have the topology information to use. But based on the transitivity of the trust, all the extended nodes should be clean because they form the trusted seeds. But after scanning with the Google Cipher browser, we found 180 domains are totally malicious. It means some of the extended nodes are already compromised, right? So it puts suspicion for every node in the graph. So we need further effort to find them and to remove them from the graph before use, right? And before I touch the methods, I'd like to highlight the difference between malicious and compromise. So for a malicious web page, it has a very obvious malicious patterns like pop-up windows, malware, or weird figures, right? But for the compromise, they are more stealthy to bypass detection. So, for example, the content of the compromised web page may be totally clean and just contain some injected URLs. These URLs are tested as clean using the existing URL checkers, right? And for the intent stealthiness, there's an example. So we found an Australian charity website got compromised because the web page contained a weird URL. The URL itself is clean, bypass all the common URL checkers, but it finally linked to a pornography website. It means that the child charity website got compromised. And the terrible result is the child charity company and the pornography content are highly connected for the searching. So we call the compromise with this stealthiness as the on-chain compromise because we needed to figure out the chain, the compromised chain, right? And the evaluation of this kind of suspicious behavior, we should extend from the one node view to a more wide global views. That's why we introduced the graph. And why the existing machine learning or topology analysis methods cannot solve the problem well? Because the first thing is the insufficient supervising information. So due to the content seriousness, it's very hard to extract some specific patterns for the compromised relevant behavior, right? The second is it's hard to have some labeled nodes. So for example, we only found 180 malicious nodes from 1.7 million nodes. So it's a very small percentage. So without insufficient supervising information, it's harder to perform the machine learning algorithms, right? The performance will be very poor. And also the ground truth for compromise is also very hard to find, right? And also existing web page or web domain analysis, either based on an individual node features or only focusing on the topology. So they will have a low accuracy and high false positive rate. Okay, now we have graph. How about graph learning? The graph neural network are good at combining the individual features and global structure informations. But here, the answer is no. Why? So first, the graph learning or graph neural networks have the scalability issues, especially in our scenarios. The graph is always with million or billion size, so it's hard to train the model. Second is the common graph learning always try to aggregate information from two-step or two-hop neighbors. But in our scenarios, the compromised behavior is always have a typical long chain of influence, like it's always from 4 to 6. So it will cause overfitting and the parameter explosion for existing graph learning models. So we have a new method. It's a two-step solution. Why two-step? Because we wanted to capture the compromised chain. It from the compromised victim to the compromised target. It's hard to find patterns for the compromised victim, but we can find some patterns for the target, like the malicious website, right? So we start from the compromised target prediction. And by the way, the malicious is just one step of the one type of the compromised target. We can also include other customized labels like the pornography, gambling, or something, right? So after we have the target predictions, we can then to find the path from benign to detected target, and then locate the victim, the compromised victim in between, right? So this is why we take two steps. The first step is the target node prediction. So here the challenge is also the limited labels, right? So we apply a graph learning scheme because the graph can make up for the lack of labels. So we design a new node ranking methods to serve as a global message parsing to aggregate information from important neighbors to refine the local predictions. So we can combine the local features, global structures, and to address the sparse label. Also, we separate the global message parsing from the local training, so we can also address the scalability issues. And after we have the prediction model, we can use the prediction value as a suspicious score. And then we find the benign node to the detected target, the path, and then we located the compromised victim using a threshold on the suspicious score. And finally, we will remove all the compromised relevant nodes from the graph before use and try to find the indicator of compromise. And the compromised victim here can be some original benign nodes, but have very higher suspicious score, right? So for the local part, it's very simple. We can just use a 2-layer fully collected neural network. And the input is also very some simple features, like some basic statistic of the URL, some vectorized features for the content of HTML, like we use the bag of words to find the word frequency as the input. The output is a probability about whether a node is a compromised target or not, right? For the global part, first we design a node ranking specific for the compromise. Why not use the page rank or trust rank? So there are 2 reasons. The first one is they always form some trusted seeds, but in our scenarios, it's harder to define totally trusted or benign things, right? Second, they suffer from the sparse initialization. So in our scenarios, for example, we have only 180 out of 1.7 million. So the initial values will be very sparse. So it's harder to convert, right? So we consider, we form the untrusted nodes and consider the compromised target as recommendations. And we try to find a recommender who strongly supports the recommendation after a few iterations of distrust backward propagation. And actually, the exact node ranking or the personalized node ranking is hard to figure out, especially for large-scale graph. So we also have approximation methods. So it can address the sparse initialization, also have some strategies to improve the efficiency, like we take the top key approximation and adaptive initialization and adaptive threshold to improve the efficiency. And finally, we can find the path from the benign to detected target and try to locate the compromised victim, and finally to remove them from the graph. So we perform 2 kinds of validations. The first validation is for the compromised target node classification. So we collect like 50,000 allowed and 50,000 denied nodes as ground truth, and try to report the accuracy of the prediction and the false positive rate. So this try to confirm the learning capability of our graph learning scheme, and also its scalability. So the second type of validation is the compromise analysis and evaluation. So here we have no ground truth for the compromised victim, but we can perform the manual check for the detected compromised victim to find whether there's some suspicious content. And finally, we can try to find the indicator of compromise here. So the basic baseline is the machine learning models on the node level data without introduce the topology, and the topology only analysis. So we test the baselines. The accuracy is around 50 to 60, and the false positive rate is around 30 to 50. So, but after applying our methods, we can improve the accuracy from 60% to 90%, and the false positive rate is around 2%. And we also compare with the common graph neural network baselines, and we have a better accuracy. And the common graph neural networks have the out-of-memory issues on our large-scale dataset. So we also try to evaluate the performance of our mechanism with different incorporation strategy regarding using or not using the topology information during training or inference, respectively. The interesting one is the inference incorporation, namely for the local prediction model, we don't touch any topology information. But during the inference, we introduce our rank-based topology information. It can improve the accuracy by 12%. It means we can improve the performance of existing machine learning model without any training. We also test the scalability of our models, and we can find that the time of the training and inference on a graph with 1 million nodes is only within 1 minute. So it's very fast. Why? Because first we separate the global message parsing from the local training. And the local model is very simple. And the training for the local model can be conducted in parallel. Also, we can further reduce the time by with just sampling 1% of the training node from the entire training dataset. And finally, we evaluate the compromise analysis. So we select 110 detected compromise victim and try to find whether there's a suspicious content, right? So we found 104 out of them have a suspicious content. So we call that true positive. The rest 6 is, we didn't call them the false positive because maybe there's no suspicious content inside, but they are at risk. For example, they use the plugin with vulnerability. So this is the work. And last month we released the children charity website. And after we informed the vulnerability, they refined the website. And then now the charity website is free from pornography content. Thank you for your time.
University are there type of motivations they sanctioned and in IP motivation to cover hack. And the signal question that if you are under with that time and ethical architecture effective models, sensible elements. But first question is our first with my so I think it's for that we claim is very simple features about URL and HTML. Why? Because we want to generate a worst case testing environment. We want to use performance of our efforts if we had very rich information about the URL and the HTML. And for our further two, now we try to introduce more information like the check about from third party skin interest charges the voice. And to be frank, our category is really considered the top level. Next to the means the line thing. The second level or fourth is sub memory for example. And working with what? It's the issue about how to store it, break the conjunction, and other ways. You refer the securities of attack, right? Attack actually observes was but hard. Why? I have many more talks of the AI security and also attacks for AI models. But in the other scenarios, its story is a little different. So first, our data is not usually data like image, text, or time series. So it's simply to index the phone reason for the AI models. Now, scenarios to include is clear feature and the origin. So maybe it's not needed to design or do this, right? Secondly, is the final prediction is not made quite release the number of features. It tries to identify the zombism from important neighbors. So maybe it can reduce the noise from a specific node, right? Maybe the hardware definitions we also introduce process. For example, we not remove only the nodes, we remove a path, right? So for example, if the checker before some predictions in between the example is UBT path, but we remove the entire path. So it also have to make to attack the mechanism. Yes. So we need to have the room for one. And I'm this so
You would detect top level enemies from the understand. Yes. So I would have in the new hand public most containing all of the different regions and the current of damage that we had because it extended maybe 2 person and 1 person from that. You are at they have just on but there is time in that. And there's no connection between the different people that will harm these from the most.
Yes, so yeah, strong papers. So what I've actually been able to start from popular interactive those or then on the Facebook or the Google because there was printed some personalized information. Maybe some customers will after some virus, right? The website fees can be trusted, like it's good. But I will be the virus site is basis. So we try to remove all these kinds of different because they care. And actually what the compromise is it's flexible. We define the malicious environment given as the target, but actually we can use more categories of the target, right? And for this sort of patches, malicious patches, actually it's known by the algorithm automatically.
Even what kind of target? As can give